In this lecture, we're going to look at a few more specifics about the sun. The general information applies to stars in general, but some of the specific information is just about our sun. Here, you can see a few images of our sun and some of its storms, seen in different wavelengths. Our sun is anything but the calm place that it seems from 93 million miles away. It's an incredibly turbulent, roiling place, and the storms that happen on the sun can affect Earth and other planets even from huge distances. The sun seems special to us because it's so close to us, relatively speaking, but it's just one of 200 billion stars in our galaxy, the Milky Way. The Milky Way looks something like this image, a giant spiral galaxy. This is not an actual photo of the Milky Way, though, as we can't take a full photo of it from the inside. The sun's position is circled here, relatively pretty far out from the galactic center. It's important to study the sun not just to understand more about space and how stars work, but it's also important because the sun affects life here on this planet. Dr. Shearer from Stanford University once said that the sun is the only star known to grow vegetables. And so far, that's true. Studying the sun and other stars may help us also to find out whether there are other locations in space that may support life. The sun is classified as a G2V star. The G means the sun is yellow. The V means that it's a dwarf star on the main sequence. We'll talk more about that later. And the 2 narrows down its mass and temperature a little from the other stars in the same group. The sun is about 150 million kilometers, or 93 million miles from Earth, and it's so large that 109 Earths could fit across its diameter, and 1 million Earths could fit inside it. Can you see the Earth to scale in this image of a solar storm? This storm is so big that the Earth easily fits within it. The sun, like the entire solar system, is about 4.6 billion years old. It is massive, and it's made up almost entirely of hydrogen and helium, the 2 lightest elements on the periodic table. The surface temperature of the sun is almost 6,000 degrees Kelvin, but at the core, the temperature soars to over 15 million. The Kelvin scale is based on absolute zero and is the same as the Celsius scale, just shifted down 273 degrees, so that there are no negative numbers. You don't need to memorize these exact numbers, but you should know that the surface temperature of stars is always in the thousands of degrees, while core temperatures of stars are always in millions of degrees. Here's an image showing the sun to scale with all the planets. Even giant planet Jupiter is dwarfed by the size of the sun. Here you see many images of the sun, many of which were all taken on the same day. Can you see the same active area in many of the pictures? The sun is yellow, but these images are a lot of different colors. Remember, many telescopes operate in areas of the spectrum other than visible light. Since radio waves, infrared rays, UV rays, X-rays, and gamma rays don't actually have color, telescopes that collect light in these wavelengths just produce black and white images. The color is just added later to make the pictures easier to see. Keep in mind, though, that the reason why the sun looks white to us is that white light is a combination of all the wavelengths of light. The sun produces all wavelengths of light, but our eyes blur them together to see white. In fact, the sun's peak output is in the green range of the spectrum, but we don't see a green sun. It might be fun, though, if we did. Here's a cross-sectional view of the sun. In the top part of the image, you can see the core of the star, where the sun's energy is produced, followed by other areas called the radiative zone and the convective zone. At the surface, we have the photosphere, the visible part of the sun. Here we can see the sunspots on the surface. The chromosphere is the part we're looking at with hydrogen alpha telescopes. From the surface, come storms like flares and prominences. We'll look at these items individually, but it's important to remember that though we're talking about the sun, all this information can be applied to other stars as well. The sun is so hot because of a process called nuclear fusion. Hydrogen atoms are the smallest and lightest atoms. These hydrogen atoms are basically just smashed together at such high temperatures and pressures that they actually combine to make helium atoms. When this occurs, a little bit of energy is released. But since the sun is turning millions of tons of hydrogen to helium every second, those little bits of energy add up. This hydrogen fusion occurs in the core. The light energy that is created has to travel outward from the core to the surface of the sun. This takes an extremely long time, though, because there are so many particles in such a small space. Each photon of light gets bumped around quite a lot before it makes it out through the radiative zone. You can see a sample zigzag path that a photon might take. Here's another image showing roughly the same process. Again, the core is where fusion happens, hydrogen becoming helium. Some estimates say that it might take a photon 40,000 years just to get through this part of the sun, but estimates vary widely. Some suggest that it may take up to 1,000,000 years. That's a pretty long time, considering that once it escapes the sun, it only takes about 8 minutes for that photon to reach the Earth. The video won't display in this animation, but you can see it if you watch it in the PowerPoint in slideshow mode. Basically, hydrogen atoms don't naturally smash together to make helium. At low temperature, when the atoms are moving relatively slowly, they would approach one another, but then be repelled from each other like this. But at a high speed, they don't have time to avoid one another, and they smash together. But it actually takes 4 hydrogens to make a helium, not just 2. 2 sets of hydrogens combine to make 2 deuterium atoms. Deuterium is a special, heavier form of hydrogen. Then, the 2 deuterium atoms combine to make a helium with 2 protons and 2 neutrons. Here is another image. At the top, 2 hydrogens, each with mass 1, combine to make a hydrogen with a mass of 2. That's the deuterium atom. The same process happens again here. Then the chain continues, adding another hydrogen to make a helium with mass 3, and then finally, the final hydrogen with a mass of helium 4, which is a normal helium atom. The main thing you need to know is basically that it takes 4 hydrogens to make a helium. You are probably familiar with Albert Einstein's famous equation, E equals mc squared. This equation is just explaining what stars are doing every second of their lives, turning mass into energy as they fuse smaller atoms into larger ones. 4 million tons of matter are turned to energy every second. This sounds like a lot, but the sun is still so big that even over its 10 billion year lifespan, less than 1% of it will be converted into energy. Here's another image showing the cross-section of the sun. The fusion process is occurring in the core. Then, the next layer out is the radiative zone. This is where the energy is produced in the core, radiates outward. Here, there are lots of particle collisions, as each photon tries to make it out of the sun. Further outward is the convective zone. Material in this zone undergoes convection, or movement in circular patterns, as hotter material rises and cooler material falls inward due to differences in density. This rolling, almost boiling motion can be seen at the surface. The animation doesn't activate in the video, but if you open the PowerPoint in slideshow mode, you can see the bubbling surface of the sun. This is because of the motion within the convection zone. These bubbles are called granules, and they can be 1 to 2,000 kilometers wide. Energy rises within the bubbles, then falls, sinking down at the edges. But this isn't just a soft, easy boil. I want you to think about this bubbling and boiling like the biggest, loudest, worst belly flop you've ever seen someone do. This hot material rises quickly and then slaps back down on the surface, causing sunquakes. Much of what we know about the sun comes from a branch of astronomy called helioseismology, which is basically studying sunquakes. In much the same way as we study earthquakes to study the interior of the earth, we can use sunquakes to study the inner workings of the sun. You can imagine the surface of the sun looking like oatmeal as it cooks. This boiling surface bubbles up and crashes back down, actually creating sound waves that can help us study what's going on inside the sun. Next to this image of granules, there's a scale photo of Earth. Look at the size of the granules compared to the Earth. Those bubbles are so large that they are about the size of the state of Texas. That is a big bubble. Just like the Earth and the rest of the planets do, the sun rotates on its axis. We can tell how fast the sun rotates by watching these dark places on the sun called sunspots. The sun's rotation is actually a lot more complex than Earth's rotation, though. The sun experiences what's called differential rotation. That means that different areas on the sun rotate at different speeds. At the pole, material rotates more slowly, making it around the sun once in 36 days. At the equator, though, material rotates much faster, rounding the sun in only 26 days. That's pretty impressive, considering the material at the equator has a much greater distance to travel, but it does so more quickly. Earth does not have differential rotation. Everything rotates at the same speed. A day is 24 hours no matter where you are on the planet. Here is an image showing you the number of days it takes for solar material to rotate based on latitude. Many solar storms and sunspots are actually a result of this differential rotation. The sun literally gets tangled up. We see that a lot of solar storms and disruptions are caused by the sun's magnetic field getting twisted because of this differential rotation. When you see looping storms like this, they are actually following the sun's magnetic field lines. The magnetic field lines on the sun are very different from the ones created by Earth. You may be wondering why these magnetic fields cause solar storms. Again, these sunspots are areas where the magnetic field is not only strong, but also tangled up. Earth's magnetic field is pretty regular around its surface, with a few exceptions we call anomalies. Earth's magnetic field lines emerge from the South Pole, round the planet, and re-enter it at the North Pole, creating a shield around Earth that protects living things on the surface from harmful solar radiation. The magnetic field around Earth closely resembles the field around a standard bar magnet. Now look at the field on the surface of the sun. It is incredibly irregular, and there are lines exiting and re-entering all over the surface, appearing all tangled up. This is due to differential rotation. The magnetic field lines literally get twisted and broken. Imagine someone with long hair riding in a convertible. The wind tosses the hair around in so many different ways, and it ends up a giant mess, and the hairs often get broken when you try to brush it out later. Magnetic field lines on the sun can snap in the same ways. Where these lines get tangled up, we get storms and sunspots. Here we see an image of the sun with several large sunspots. The second and third images are sunspots up close. These spots look small compared to the size of the sun, but they can actually be the size of Earth and even larger. These sunspots look dark compared to the rest of the sun because they are cooler than the rest of the sun, but they're actually quite bright. If you could magically move a sunspot and put it in a different area of the sky, they'd actually be brighter than the full moon. Note that cooler doesn't mean cool. They are still incredibly hot, just not as hot as the rest of the sun. They can live for a few days up to several weeks. Much like shadows created in eclipses, the darkest center part of the sunspot is called the umbra, and the lighter shadow around it is called the penumbra. Here you see a family of sunspots as they move across the sun's surface over the course of several days. This is how we can measure the rotation rates of different areas of the sun. Equatorial spots move a lot faster than spots nearer the poles. Here you see side-by-side images of the solar disk with sunspots and a photo showing the strength of the sun's magnetic field in different locations. Notice that the sunspots are occurring in areas where the sun's magnetic field is strongest. The black regions are magnetic south and the white areas are magnetic north, so you can see that they always come in pairs. These pairs occur because they are areas where the sun's magnetic field is emerging from the surface. These sunspots are areas of strongest magnetic field, and storms often follow these magnetic field lines between sunspots. Though you can't see the magnetic field lines with your eyes, the hot ionized gas of the sun moves along the magnetic field lines and allows us to see where they are. These loops of material are called prominences. If you search for solar prominence on YouTube, there are a lot of neat videos that show different forms of these solar eruptions. The sun's magnetic field varies over an 11-year cycle. It varies some. It's not always exactly 11 years, but it's pretty close. So over an 11-year period, the number of sunspots rises to a maximum point, then falls to a minimum point, then begins to climb again. Notice that some peaks are higher than others, so one solar maximum isn't necessarily comparable to another. The last solar minimum was in 2019, and the next solar maximum is predicted to be around 2025. Notice that there was a period in the late 1600s where sunspots basically disappeared for quite a while. This was during a time period called the Little Ice Age. It's not known whether solar activity is solely responsible for this event, but there does seem to be a correlation between sunspots and climate events here on Earth. There are some people that suggest that the climate change, sometimes called global warming, that Earth is currently experiencing is due to changes involving the sun. This, though, is unlikely, as the climate change has continued to warm in a time when sunspots have actually been decreasing. Here are a couple of images, one pair in ultraviolet light on the left and another pair in visible light on the right. These are showing changes in sunspot activity over only a 3-year time span. Notice in the visible light images, the bottom right, just how many more sunspots there are than in the upper image. In the UV images, where the sun appears green, you can tell just how much more active the sun is at solar maximum than solar minimum. The number of storms is greatly increased. In the next two images, compare the activity level of the sun in the X-ray part of the spectrum with the activity level on the sun's magnetic field. This is the image in X-ray. See how active it is at solar maximum here, and how it decreases over time to solar minimum here, and then increases in activity again to here. Notice that we have a similar pattern here. Activity decreases, then increases. Let's flip back and forth between those images again. Here was the first one. You see that the high magnetic field energy areas match up with the areas that are highly active in X-rays. Areas that are active on the sun in one part of the spectrum are also active in the other areas of the spectrum and other types of energy as well. Here is one more image showing change of X-ray activity over time. The images on the left in the foreground are at solar maximum, and those farther around the path are approaching solar minimum, where there is almost no activity at all. This is all over only a 4-year time frame. These are similar images taken by a different spacecraft over 2 full solar cycles. Notice the pattern of increasing and decreasing activity as you trace the path from 1996 to 2020. At the bottom of the page, you can see a couple of different images that were taken several years apart. Notice that on the lower left image, there are a greater number of sunspots. They're relatively small, and in the right image, though there are fewer spots, the major one is quite a bit larger. Notice also that in the lower left image, the sunspots are clustered both above and below the equator. Sunspot numbers and intensity vary over time, and they vary pretty regularly. Take a look at the graph at the top, sometimes called the butterfly diagram. This is graphing the number and intensity of sunspots against latitude. The line in the center is almost vacant. There are very few sunspots actually at the equator, while they cluster strongly in lower latitudes and are almost absent again in the polar regions. We already looked at the fact that the core is a lot hotter than the surface of the sun. That seems reasonable, as Earth's core is much hotter than its surface too. However, notice that as you leave the surface of the sun and travel through the atmosphere, the temperature spikes up again. The reason for this dramatic temperature increase in the corona is still not fully understood, but is likely related to high amounts of X-ray radiation detected here. The photosphere is what we ordinarily call the surface of the sun. This layer is about 300 miles thick, and the temperature is about 550 Celsius. This temperature is what determines the color of the star. The chromosphere is the lowest level of solar atmosphere. It's reddish, meaning that it's just beyond the red part of the visible light spectrum, but is invisible to our eyes. You need a hydrogen alpha telescope to view this layer. In this image, notice the light and dark spots showing high levels of solar activity. Notice also the bits of material that are leaping up off the surface. Storms on the sun that leap up, arch across the magnetic field lines, and fall back to the solar surface are called prominences. They may last only a few hours, but can last for much longer periods of time. These storms are enormous. These loopy storms are not a danger to Earth as long as the material continues to fall back down to the surface of the sun. But that doesn't always happen. Sometimes prominences rip off the sun's surface and send material flying out into space. If you watch the PowerPoint in slideshow mode, the lower left picture is an animation showing the flare being released by the sun. These flares usually occur in areas of high solar activity near groups of sunspots, and these storms can release as much energy as 1 billion megatons of TNT. That's far more energy than what is needed to power the entire Earth's power grid for many centuries and would be equal to about 62.5 billion Hiroshima bombs. The sun is so much larger than Earth that Earth is dwarfed by the size of these storms and would appear about this big in this image. These sorts of storms are quite common during periods of high solar activity at solar maximum. These storms can occur suddenly and affect us here on Earth by causing power outages and shorting out satellites. Here's an image of a coronal mass ejection. Here, a huge bubble of gas is escaping the corona, a layer of the sun's atmosphere, and is being released into space. These energetic eruptions, like flares, can also affect us here on Earth. The major difference, though, is that a solar flare comes from the sun's surface, and these CMEs come from the atmosphere. These ejections move more slowly than the speed of light, taking a couple of days to make it to Earth. Ordinarily, the Earth's magnetosphere protects Earth from the solar wind, the natural stream of charged particles coming from the sun. But these powerful releases of mass and energy can disrupt the normal flow from the sun, disrupting satellites, GPS systems, cell phone systems, and can even take down portions of the power grid, causing blackouts. One solar storm back in 1989 caused blackout conditions in a large area of Canada and the US. A 90-second storm caused 6 million people to lose power for 9 hours. Another storm was so powerful that it killed some instruments on NASA's Mars Odyssey probe, another 50% farther from the sun than the Earth. This shows you just how extensive the damage was across the U.S. from the '89 flare. Though the blackout was in the northeast United States and Canada, equipment as far as California was tripped. Moving farther out from the sun, you come to the sun's corona. Although it can't ordinarily be seen, it is visible from the Earth during a total solar eclipse that blocks out the solar disk. An instrument called a coronagraph can use a metal disk to block the light of the sun, creating an artificial eclipse to study the sun's corona. Here is another image of the corona during a solar eclipse. Notice just how far out the streamers reach beyond the edge of the sun. It can extend for millions of miles and reach 1 to 2 million degrees Celsius. This is an image of a telescope equipped with a coronagraph. This metal disc covers the brightest portion of the sun so we can see the faint corona. Notice the pictures on the right side and the difference between the amount of corona visible depending on how active the sun is at a given time. And finally, we have the solar wind, the gas that streams off of the sun in all directions at about 1 million miles per hour. The wind originates in the corona, which is so hot the sun's gravity just cannot hold on to this plasma. The solar wind actually changes the shape of Earth's magnetic field, compressing it on the side toward the sun and stretching it out on the side facing away from the sun. As the solar wind's speed fluctuates, storms can be produced in Earth's magnetosphere. The solar wind is composed of charged particles. The northern and southern lights, called aurora, are caused by this high-energy radiation interacting with the atmosphere. Here you see greenish lights that dance around in the sky. But aurora aren't always green. The color is determined by the element that is being interacted with and the altitude at which it occurs. When the sun generates conditions in space that have the potential to seriously affect Earth and other planets, we call these conditions space weather. Just like meteorologists on Earth, there are people who monitor space weather, watching out for solar storms that can endanger us here on Earth. Besides triggering beautiful auroras, these solar storms can damage satellites, disrupt power grids and electrical systems, interfere with cell phones and other communications, and disturb animal movements. They even threaten astronauts and high-flying airplanes with their radiation. Scientists are working to predict the occurrence of solar storms, much like meteorologists predict weather on Earth. In fact, a powerful event may cause $2 trillion in damage in just the first year, according to the U.S. government, and take 4 to 10 years for the planet to recover. Here are a couple more images of aurora, the beautiful displays of color in high-latitude skies. They're caused by high-energy particles from the solar wind becoming trapped in the Earth's magnetic field. As these particles spiral back and forth along the magnetic field lines, they come down to the atmosphere near the north and south magnetic poles, where the magnetic field lines disappear into the body of the Earth. The greenish yellow or red color is caused from the interaction with oxygen molecules, whereas any blue color is visible from the interaction with nitrogen molecules. Since the Moon and Mars have neither atmosphere nor magnetosphere, astronauts are at a significant risk from solar radiation and X-rays. Had astronauts been traveling to or walking on the Moon or Mars during solar storms of October 2003, they would have received a lethal dose of radiation. Aurora are not unique, though, to Earth, as the gas giant planets also have these colorful displays. About 60 kilometers or 40 miles above us lies a region of our atmosphere we call the ionosphere. The ionosphere has a strong influence on the propagation of radio signals. Long wavelength radio frequencies bounce off electrons in the ionosphere, allowing radio communication over the horizon and around our curved Earth. The ionosphere reacts strongly to intense X-ray and ultraviolet radiation released by the sun during a solar flare, solar storm, or coronal mass ejection. The density of the particles in the ionosphere is altered during such a storm, changing the wave's ability to bounce and resulting in the intermittent static or loss of reception from distant communication stations. And here are a few more places you can go if you're interested in learning more about solar storms and their effects on Earth and other planets.